In section 16.1, we derived the few expressions for a Hertzian dipole. Now we're going to use those expressions to understand the physics of a Hertzian dipole antenna. And at this the very beginning, let's just focus on the near field zone where the position, the R location, is very small compared to the radiation wavelength. So we'll be talking about the physics very close to this dipole. So first, let's copy down all the field expressions from the last session. We have ER, we have E theta, and we have H phi. If we have the beta R much less than 1, so this means that this term is going to be small compared with this term. And also the phase beta R is going to be a value very close to 0. So this means that the exponential minus j beta R can be approximated as 1 in this expression. So the R component of electric field becomes this expression. Also, let's do the same approximation to these field components. So we cross out this term and also this term. Just keep this significant term in this expression and also allow this phase term to approximate a value of 1. Then you have a simple expression for the theta component of the electric field. For the magnetic field, we also do the same thing. So you get a phi component of the magnetic field described by this expression. And I want you to pay attention to this, Ga, the imaginary unit in E theta, because if you want to know the radiation along R direction, then we're going to cross E theta with H phi to calculate the Poynting vector along R direction. But when we take the real part of this expression, we found that you have J here, and this is the real number. So it turned out that you don't have anything left in this calculation. So this means that if we pay attention to the near field of a Hertzian dipole antenna, turn out that those fields do not radiate. And this is the quite interesting phenomenon because in the near field, those fields dominate, but they do not radiate. So let's look into the near field patterns. But this is non-radiating field is very similar to the dipole field. So let's recall the relationship between charge and current, and also pull out the definition of the dipole moments. With these two, we can rewrite the theta component of the electric field to be an expression containing the dipole moment. We can also rewrite the R component of the electric field containing this dipole moment. And let's make a comparison between this field and a static dipole field. Turn out that those fields are all the same. So this means that in the near field zone, Hertzian dipole antenna will have the same electric field pattern as a static dipole. So this is the field radiated from a Hertzian dipole antenna. If you look into the near field zone, then you see that this field pattern is going to be the same as the field pattern for a static dipole field. And this is not going to be useful because the field, they do not radiate. So we just try to calculate the Poynting vector along R direction, and we found that there's no average power based on those dipole fields. But if we focus our attention in the far field zone, the story can be very different. Now, beta R is much larger than 1, so those 1 over beta R terms with higher power are going to be small compared with the first order term. So for the theta component electric field, we cross out the last two terms and just keep the first term, and then we have the dominant term 1 over beta R for the theta component of the electric field. Well, let's do the same thing to the phi component of the magnetic field, and then we cross out the small value term and just keep the first term here, and then we have this h phi. And you see that the E theta and h phi are in phase. Both of them has j in front of it. So this means that when we calculate the Poynting vector, you're going to get some net value radiating along r direction. And we can also calculate the r component of the electric field. But when you cross out the third order term, you can only keep the second order term. Compare with all other first order term, this second order term is going to be small, so that's just right r component electric field to be almost zero compared with these two terms. And so if we do a ratio of this E theta to this h phi, we also found that the ratio is equal to the intrinsic wave impedance, just like a plane wave. So indeed, these two field components are radiating in space and propagating in space. So if you again take the E theta cross with h phi conjugate, and then the real part of it is not going to be equal to zero. So this means that there will be some net power flow along the radial direction. So indeed, such construction of the charge, oscillating charge, can produce radiation in space. On the last page, we have the far field expression for the theta component of electric field and also phi component of the magnetic field. So we can calculate the average power density along r direction. So if you complete this calculation, you'll be having this expression for the magnitude of the complex Poynting vector, which is the average power density along r direction. And you can see that this expression depends on the square of sine theta. And you can plot the surface of the sine squared theta in this polar coordinate system. And this diagram will tell you there's very little radiation radiated along z direction. But the strongest radiation is going to be transverse to this dipole axis along the theta equal to 90-degree direction. Another thing we can see from this expression is that this power density is inversely proportional to r squared. So this means that if you do a surface integration about this dipole antenna on a sphere, then you can cancel out this r squared in this expression. So the total power radiated by this dipole antenna will be a fixed value independent of the position of r, and this is based on the energy conservation. And sometimes it's easier to cut this donut into different shape so that we can analyze the intensity of the radiation. For example, if we cut this donut shape of radiation pattern at a location where the phi angle is a constant, then you end up having two circles like this. And we call this E-plane patterns of the radiation. But if we cut this donut with the horizontal plane like this, then you're going to have this radiation pattern. We call this H-plane pattern. And this plane is defined by theta equal to pi over 2. And from those patterns, you can tell where you have the strongest radiation and where you don't have radiation. For example, from this E-plane pattern, apparently you see no radiation along the dipole axis direction. But from this H-plane pattern, you see symmetry of the radiation about the dipole axis. And at 90-degree direction, you have the strongest radiation. 所以呢，在这个16.2节里头，我们介绍了几个这个 Hertzian dipole 的一些特征。在进场的这个地方呢，它的电场呢，跟这个静电场的 dipole 的这个场呢是一样的。那 这些场呢，在这个进场里头的这些电场跟磁场，它不会产生 radiation。虽然它主要的场是来自这个static 的这个 dipole electric dipole，但在原场呢，它这些场这个电场磁场它是往外一直的辐射出去，那它的 radiation intensity 呢，看起来像一个甜甜圈的一个形状。然后呢，这个甜甜圈的形状告诉你说，在 dipole axis 的方向呢，它是没有辐射的，但是呢，在这个dipole axis 的这个垂直方向上头，这个辐射的强度呢会是最强。所以这是第2小节里头要跟大家做的这个介绍。谢谢。